Okay, so we're looking at velocity time graphs, and we're going to do some calculations based on these guys. So the first thing, initial acceleration. Initial meaning the starting or the very first acceleration. So if I use that word, I'm just talking about the slope of the first line right here, that rise over run right there. So you can just look at it and probably just see what the answer is. I didn't make the graphs complicated. Starting at 0, 0, we go over 1 up 2. Right? Over 1 up 2. Over 1 up 2. Over 1 up 2. So just eyeballing it, you can tell the accelerations should work out to be positive too. We'll do the calculation though, so you know what it is. Insert a new page in here. Question 1. Acceleration is the slope, okay, the rise over run. So if you want to stick with the slope formula, just you can use it. The second y value is 6. Initial y value is 0, or I should say velocity value, right? But we tend to think in x and y with slope. And it does that 3 minus 0, or 2 meters per second squared. Just because we're doing the formula for slope doesn't mean we're changing our formula for acceleration. It's still final velocity minus initial divided by the time it takes for that to happen. Right? We're going final velocity is 6, initial velocity is 0, final is 6 minus 0 and takes 3 seconds. So we're not changing up any of our physics or concepts. We're just looking at it with a more mathematical eye. And so skipping question 2, going down to question 3. Question 3 is asking to calculate the total distance traveled east. Total distance traveled east is the area contained above the time axis. So the time axis is the horizontal axis. The area contained above that is the distance traveled east. So there's only one section, a large trapezoid right here. Okay. That entire area, you don't have to fill it in on your copy because we're going to, but just showing you. That entire area represents the distance traveled east. Erase that up. Now, some people like to break up areas into triangles and rectangles, and that's fine, it will work. But you can do this calculation in one quick calculation by using the trapezoid one. The formula is in your handbook. There's a sheet of paper in your handbook with all your geometry shapes. So I'll write it out here. So the area of this thing is the height multiplied by two bases, or B1 and B2. B1 plus B2. I'll label them in a second here, divided by 2. Looks complicated at first. The height is the distance between the parallel lines. The bases are the lengths of the parallel lines. It doesn't matter which way you number them because you're adding them together, so the math doesn't matter. And then dividing by 2. So for this one, it's going to be 6 multiplied by 10 plus 5, and then divided by 2. So the 10, I'm just counting squares. Now, I'll keep things simple with the numbers by only incrementing by 1. But if you happen to be using a scale where maybe every square is 5, make sure you use the units that are on your scale. Don't just count squares necessarily. I'm going to try to keep it consistent, but if you're doing a problem from your textbook, it might go from like 0 to 10, 20, 30, 40. And if it does that, you have to use those values. You have to use the values that are on your graph. All right, so let's calculate it out on the next page. So the distance traveled east is that area on the top, which is the trapezoids. I'll write the formula down for trapezoid. Height times B1 plus B2 divided by 2. So for us, the height was 6, just the distance between the parallel lines. First parallel line was 5, next one was 10 divided by 2. So that's 15 times 3, 45. So the distance traveled east is 45 meters. Question 4. Question 4 is asking us to calculate the distance traveled west. Distance west is the area contained below the time axis. Now, you have to be really careful here. Very common mistake especially when looking below the time axis, is to shade in or look at the incorrect area. It has to be between your graph lines, the actual graph of the data, and the time axis. A lot of people end up doing this area as well, like for some reason. They kind of do that. This area down here is not contained by any of your graph lines. So you can only use the area contained by your graph lines. All right, so we're going to do another trapezoid, a little bit smaller. It's going to have a height of 3. I'll label it height of 3. Top row is 10. Bottom one is 9. So it's going to be 3 times 10 plus 9 divided by 2. Go right out. So this is the distance traveled west. Okay, so we just broke it up into 2 parts. So it's the bottom area. Bottom area. So I'll write the formula again so we have it. Okay, doesn't like to write right there. By 2. Height of 3, 10 plus 9 divided by 2. So that's 19 times 3. But what is that? 20 times 3, 60, 57 divided by 2, 28 and a half. Feel free to ask questions anytime if you're stuck or something doesn't seem clear. Just doing area calculations. Notice my numbers are all positive. I'm working in the negative area of the graph, but when I'm doing these calculations for area, always positive values. Okay, so do not go -3 multiplied by this. Okay, we're just breaking up into different distances, so just use positive values. Question 5, calculate the position at the 20-second mark. So we're looking at where did it end up at the 20-second mark. Where is it at 20 seconds? So there's not much work to do now. We've already done the setup for this. We figured out the distance traveled east. We figured out the distance traveled west. The final position for a problem like this is the area on the top minus the bottom. So the area on the top minus the bottom. So we have 45 from the top minus the 28.5, and that's 16.5 meters. So this object drove, if it's a car, drove 45 meters east. That's when it turned around and then drove 28.5 meters west. Ends up 16.5 meters from its starting point. So remember, all these equations and all the information that I'm using, they're in your handbook. It's like the second page in or first page in. So don't forget, check with that first before you come and waste time with your hand up in the air because you don't know what to do. Check your handbook first. You're going to have access to that. Question 6, average velocity and speed for 20 seconds. So average velocity, we'll do that one first. That's where the object ends up going from where it started. Starts at 0, ends up at 16.5. Took 20 seconds. So that's approximately 0.83 meters per second. It's a quick reminder that the displacement change in position, I'm getting that value by doing the final position minus the starting position. Right? The final position is 16.5. Starting position is 0. Right? So 16.5. Just in case you don't know where I got the value from. So now speed will be a little bit more work, but not too much. Average speed is distance over time. We didn't calculate the total distance traveled, but we have all the pieces. We have the distance traveled east, 45, distance traveled west, 28.5. So we add them up. So it's 45 plus 28.5. And that took 20 seconds. So it's 73.5 divided by 20. So the average speed for the whole thing works out to be 3.68-ish meters per second, somewhere around there. 3.68. Questions on what I'm doing with the numbers, where I'm getting them? All right, so speed, total distance, distance traveled east plus a different distance west. Remember, distance, scalar, direction doesn't matter. Velocity, where it ends up matters. So remember, average velocity communicates and tracks where an object is at any point in time. So knowing things like average velocity and acceleration, things that are vectors, it tells us where it is, and we can calculate where it is from a position. Speed and distance, we have no idea where it is. We just know kind of how fast it went on average in terms of total length divided by time. So again, if you're worried about fuel consumption or putting kilometers on a vehicle, distance matters. One more question to do, and we're all done. Question 7. Calculate the acceleration at the 9.31 second mark. I like putting a question like this in here just to make you kind of think about what math slope is again. If you find the position 9, it's right about there. 9.5, you can eyeball that. There's 9.5. There's no way you're going to be able to put your pencil on 9.31, but you know where it is. More importantly, you know which line it hits. Not which horizontal line from the graph grid, you know which line it hits from the data, from the information being displayed. Okay? It hits that one. The acceleration at any point in time is the slope of the line. You do not have to use the point I'm giving you in the question. You don't have to use 9.31. You can't see exactly where it is. You can't get a good read. So any single point on this line, any single point on that line has the same slope value. Right? Or any 2 points, I should say. It's things you've done in math before. If 2 points lie in the same line, they have the same slope. So I'm going to use the starting point and the ending point at the corners. And you can, this question, you can eyeball it. We go down 3 over 1. Right? Then we go down 3 over 1 from there. Right? Down 3 over 1. So the slope should end up being -3, but we'll calculate it so you can see the math. So we can do the acceleration formula, but from a velocity time graph. So it's a slope. It's the slope of the line that it hits. You don't have to use the exact point. Right? The slope of that line. Well, the 2 points I'm looking at, the first point is, see down there, the time value comes first. That's 11. But I'm just gonna label those points so you can see them. You can do the same thing if you want to. So I'm going to use this point, which is 11, -3, and up here, that is 8, 6. You do the math between those 2 points. So if you do y2 minus y1 over x2 minus x1, your y2 is -3, your y1 is 6. It will do the it will do the acceleration formula for you. That's what you're doing. But here we're just going to work it out with slope. So it's -3 minus 6, so final velocity minus initial, looking at just this point, just this segment in time, 11 minus 8. So in 3 seconds, its velocity changed by -9. It just means it went from +6 to -3, so the change was -9. It's a negative slope, so the acceleration is -3 meters per second squared. There's a little bit of confusion in earlier periods with this, but any questions on what I'm doing? I'm just calculating the acceleration during part of this object's motion, right? Specifically between, the 2 points given on the graph, or between 8 and 11 seconds. Okay? So it's not an average acceleration, it's just the acceleration between these 2 points in time. Well, I guess it is like an average. Okay. All right. Save it.